Welcome to today's lecture, 28th lecture of nuclear astrophysics. Can you recollect quickly what I have discussed in the previous lecture? Survival of carbon-12 nucleus, survival of carbon-12. Before that I have discussed the creation of carbon-12, and these two topics were discussed after I have covered the PP chain and CNO cycle. So, why we are discussing all these reactions? I think it makes sense if we remember these things, fundamental and very important things regularly. Nuclear astrophysics, which is the union of nuclear physics and astrophysics, is a subject which helps us in twofold. Number one, the energy produced from the stars including the sun, how to calculate them. So, the amount of energy produced at the different stages of stars evolution, stellar evolution, we need to understand the nuclear reactions. That is where nuclear astrophysics comes into picture. So, not only this, not only to understand the energy produced in the stars and during the stellar evolution, but also totally different goal, that is synthesis of elements. In the universe you see so many elements, isotopes and isobars around you, and star, majority of the nucleides you can find in the star. So, it is a hub of the elements. So, it is like a cooking the nucleides inside a star. So, the topic that we are discussing, PP chain, CNO cycle, creation and survival of carbon-12. So, at certain stage we see the energy produced because of some reactions, but mostly I am saying mostly we are covering the synthesis part. What kind of nucleus is produced because of which type of nuclear reaction, that is what we have been discussing, right. So, in today's lecture when I say recap, in the survival of carbon-12 we have seen how nuclear reactions should happen so that the ratio of carbon to oxygen should be maintained, that is 0.6, C by O is 0.6, right. And then how the helium burning phases are blockened because of some reasons, right, and what are the perspectives of helium burning. These are the things which I have discussed in the previous lecture, all right. In today's lecture, I am going to cover a few more stages during the stellar evolution, which covers many types of nucleides, how they are synthesized, all right. So, after I have discussed carbon creation and survival, all right. Now, in today's lecture I will discuss how this carbon burning leads to the synthesis of different nucleides, carbon burning, all right. So, I am discussing the advanced stages in the burning during stellar evolution. Of course, I am completely below the iron peak, I have not yet crossed the iron peak, thus I have not yet crossed the discussion on synthesis of elements beyond iron. So, I am discussing only below the iron peak, if you consider the binding energy curve, all right. So, in the advanced stages of advanced burning stages of the stellar evolution, if you consider after hydrogen and helium burning, what are the burning stages that comes into picture? It is carbon burning, then I will discuss neon burning, then oxygen burning, then silicon burning, all right. So, these four types of stages, burning stages, I am going to cover in today's lecture, okay. So, in the previous chapters we have discussed thermonuclear reactions in the interior of a star. They start with hydrogen burning, right, they start with hydrogen burning and energy keeps on producing. So, once hydrogen is exhausted, whatever processes are taking place, they are leading to heavier elements, not only heavier elements which is simple to understand, but more tightly bound nuclei. So, this is the important thing you have to understand. In the interior of the star, which starts with the hydrogen burning, it leads to the formation of elements which are more tightly bound when compared to the hydrogen, and also heavier elements they are found, right. And the burning of these heavier elements, which are tightly bound nuclides compared to hydrogen, they emit energy which we call as nuclear energy. So, there has to be a balance between the nuclear energy and the gravitational energy, so that evolution of star happens, goes on smoothly. The moment we find any imbalance, what will happen? Either star will collapse, or the star will completely contract, goes to the white dwarf stage, or it will go to the explosion stage like supernova. So, these two extremes I am going to discuss in today's lecture. These two extremes I am going to discuss in today's lecture. Okay. So, let me give you a brief background of advanced burning stages in the star. All right. As I said, starting with the hydrogen burning, the star's core transforms into heavier and more tightly bound nuclei. So, these 2 points we have to remember. Now, the energy produced in the nuclear reactions, it will help the star not to collapse against the gravitational effect. Now, starting from the hydrogen, after one fuel is exhausted, what will happen? There will be an imbalance between the thermal pressure and the gravitational force, because the temperature is not yet enough to ignite the other things. So, what will happen? Because of this contraction of the star's core will occur. Now, the contraction of the core lead to the increase in the density and increase in the temperature. This I am repeating many times, because this happens continuously in the star. So, in the lectures you will come across these words many times. I am going to repeat these words many times. Okay. So, the contraction of star's core, it will help in the igniting the ashes of previous burning stage. For example, if you consider ashes of helium burning leads to the formation of nucleids whose mass numbers are greater than 20. For example, in the helium, after this helium burning, you will find the elements carbon, neon, oxygen, silicon, and then we can also discuss this explosive burning. All right. Now, there is an interesting question. When I say burning of carbon, burning of neon, burning of oxygen and burning of silicon, they are happening in every star. All those reactions are happening, all those burning phases are happening, maybe, may not be. Who will control or who will tell us whether any particular burning phase is happening within the star or not? Who will tell us? It is the mass of the star. So, you can realize the importance of the temperature in terms of energy, importance of temperature in terms of the gamma peak width and the gamma peak centroid. At the same time, you can also realize the impact of mass to explain whether or not all these burning stages will happen inside a star or not. How they can explain? Let us see. Okay. Very soon I will explain. Now, all these burning stages, in what time scale they are happening? Whether their time scales are shorter or longer than hydrogen and helium burning. Of course, we can easily expect they are shorter than the hydrogen and helium burning, right, because of larger loss due to the neutrino emission. As you go towards carbon, neon, oxygen, silicon, the number of neutrons emitted, it is very high. Because of that, the time scales of these burning stages, they are shorter than the previous stages. All right. Now, in the explosive phase, what will happen? In the explosive phase, whatever heavier elements are formed, they will be, there is something called as propulsion of these heavier elements in the interstellar space. Propulsion of heavier elements in the interstellar space. And which we call it as supernova, right. The propulsion of heavier elements in the interstellar space, after that what will happen? New stars will be formed. How? This propulsion of heavier elements in the interstellar space, they will mix with ashes of other stages, okay, giving rise to formation of new stars. So, this is how hydrogen burning, helium burning, carbon, neon, oxygen, silicon, and then explosive burning which takes place at higher temperatures. And once the star reaches to this stage, I have not yet discussed what will happen if it is not going to the explosive stage, that I will discuss in the next slide. All right. So, once the star reaches the explosive stage, the heavier elements will be propelled into the interstellar space, and wherever they are going, they will react with the ashes of the previous burning stages at that place, and slowly a new star is formed. So, this is how stellar evolution take place and how supernova helps in formation of new stars. All right. Now, let us see the carbon burning. So, I have given you some overview of advanced burning stages. So, let us start with the carbon burning. Why only with carbon burning? Why not others? Very simple to imagine, isn't it? You see, the burning of hydrogen and helium, when it is over, then what will happen? You can imagine some kind of, I am drawing the cross sectional view. Okay. So, this is the cross sectional view of this star evolution. This can be considered as carbon and then oxygen, right. Carbon and then oxygen, they are occurring within the core of the star, Where from this carbon and oxygen have come? Because in the core, when helium is exhausted, what are the ashes of the helium burning? Yes, do you remember? Alpha plus alpha, we have seen it is beryllium, and alpha plus beryllium gives rise to carbon 12, right. Now, in the helium burning stage, whenever a carbon is formed, you have plenty of alpha particles which reacts with carbon, which gives rise to, all right, 16 oxygen. So, once helium is exhausted, what you have is carbon and oxygen in the core. So, that is why in the core I have written carbon and oxygen. Now, around this core you can see a shell of helium. This is called as helium shell, all right. And around this shell there is a open region, envelope of this envelope surrounding the helium shell, this is called as helium envelope. And around the helium you can see this is the hydrogen, see. So, once hydrogen and helium, they are exhausted within the core of the star, do not think that they are completely gone, no, they are around the core. So, as I have discussed, if you remember in the helium burning, now I am discussing carbon burning, but just recollect what I have discussed in the helium burning. Once hydrogen is exhausted, helium is there within the core, all right, and around the helium core we were discussing about the hydrogen burning in the shell, right. Similarly, once helium gets exhausted, then around the core within which carbon and oxygens are there, because they are the ashes of helium burning. So, around the core you have helium shell. Not only that, as it expands, you can always imagine helium envelope. Now, around the helium you always have this hydrogen, all right, hydrogen shell, okay, hydrogen shell, and then you have this hydrogen envelope. So, this dashed region is hydrogen envelope, So, this is the hydrogen shell basically. So, burning of hydrogen and helium, they continue around the core within which we have carbon and oxygen. But now, our main motto is to discuss carbon burning, all right, and ashes of helium burning, they are the carbon and oxygen 16. Now, the question comes into our mind, see carbon 12 and oxygen 16, they are available, who will burn with faster rate? Okay. So, which one has to be considered as the next stage of the burning phase? Very simple. See, the reaction between carbon oxygen or oxygen oxygen, if you consider and if you do the calculation, Coulomb barrier will be less for the carbon 12, is not it? So, it is the carbon burning which comes first before the oxygen burning. Now, in the previous lecture I have told you C by O lecture that the ratio of carbon to oxygen, that is 0.6. This decides the future of the star when you have carbon and oxygen here. Okay. So, this I want to mention because the ratio of carbon and oxygen I have discussed in the previous lecture. Interestingly, the first fusion between heavy nuclei in the stellar evolution is here with us, and that is carbon plus carbon. Why I am saying it is a first fusion reaction between heavy nuclei? Because till now whatever reactions we have discussed, either it is proton plus proton or proton plus carbon, alpha plus oxygen, everywhere you are coming acrossing lighter particles, lighter species, right. So, light species were involved until now, whatever reactions have been discussed. For the first time we are discussing a reaction where two heavy nuclei are involved, because in the core there is no helium, only carbon and oxygen are there. So, either you have to assume carbon plus oxygen or oxygen plus oxygen, and as I have said, it is because of the Coulomb barrier consideration, due to which one has to consider the carbon plus carbon. What is the compound nucleus when carbon reacts with carbon, right? It is magnesium 24 in the excited state. If you do the mass difference calculation, it comes out to be 14 MeV. It comes out to be around 14 MeV. You can see the level of excitation within the magnesium, the level of excitation within the magnesium, all right. So, you can easily expect large number of overlapping states, because the excitation energy is say 14 MeV you are coming crossing, right. So, you can expect large number of overlapping states, and the reaction of carbon plus carbon proceeds through this large number of overlapping states of magnesium, right. Not only these two, when carbon plus carbon 12 gives rise to magnesium 24 in the excited state, and when the reaction proceeds through these overlapping states, what are the outcomes, what are the products? Well, there is more than one possibility. Number one, it can emit proton along with 23 sodium, it can emit alpha along with neon 20, it can emit neutron along with magnesium 23. So, you see now we are getting this lighter species again, proton, alpha and neutron, is not it? And the corresponding Q values are shown here, positive Q value, negative Q value. So, for neutron emission we need to supply 2.6 MeV to carbon plus carbon, so that neutrons are emitted. So, whenever time comes I will show reactions which are the sources of neutrons, all right. Not only these three, two more reactions are possible. Number one, it is a radiative capture kind of thing, carbon 12 capturing carbon 12, giving rise to Mg24 in the very high excited state. During de-excitation only gamma comes out, or magnesium 24 can break up into beryllium 8 and oxygen 16. Magnesium 24 can break up into beryllium 8 and oxygen 16, they are also possible. So, overall how many reactions are possible when carbon and carbon react with each other, when they go and undergo fusion with each other? 5 reactions are possible. Out of them, 3 reactions emit lighter species and 2 reactions emit one gamma and another beryllium 8, but they are not of very importance in the energy production, but they can give us an idea about the synthesis of different nucleides, all right. Now, continuing the discussion on carbon burning, depending on the mass of the star, please understand the temperature region over which this carbon burning take place. It is 0.6 to 1 gigakelvin. Now, slowly I am increasing the temperature, right. If you remember, for alpha plus alpha, the reaction during the triple alpha process, when we discussed the Hoyle state, it was the T8, even if it is a little bit greater than T8, then alpha plus alpha can happen. So, that was the temperature region. Here the temperature region, if you see, 0.6 to 1 for carbon burning, okay. And the explosive carbon burning can happen in the temperature region 1.8 to 2.5 gigakelvins, all right. Now, one of the very interesting aspect in the carbon burning, the role of mass, Please recollect what I have said some time back. Whether or not all these burning stages will happen or not depends on the mass of the star. Okay? Whether or not the burning stages will happen, it will be decided by the mass of the star. Now, you might be aware of a very important quantity, that is Chandrasekhar limit. Chandrasekhar limit says that if the star mass is less than 1.4 times that of mass of sun, in terms of kilograms we can say it is 2.7 into 10 to the power of 30 kg. If it is less than that, what will happen? Okay? So, if the less than, we can say 1.4 m naught, m sun, then the central core does not have temperature enough to ignite the carbon. Listen carefully. If the mass of the star is less than the 1.4 times of the mass of the sun, whatever temperature is available within the central core, it is not sufficient to ignite the carbon. So, what will happen? The contraction of the core continues and the density will increase. See, no carbon burning does not take place now, but the contraction of the core leads to the increase in the density, and whatever thermal energy is produced, it will radiate away from the core. And when majority of the thermal energy is radiated away from the central core, what will happen? The electron degeneracy, which is a quantum mechanical phenomenon, the electron degeneracy will exert pressure to balance the gravitational collapse. Okay? To balance the gravitational collapse, electron degeneracy will exert some pressure. Now, what will happen is the star becomes stable. This state of the star is called as white dwarfs. Where we have used this word? When we discuss the HR diagram, okay? When we discuss the HR diagram, this is the main sequence and this is the white dwarfs, right, WD, and here we have super red giants, isn't it? So, white dwarfs, they are formed when the mass of the star is less than 1.4 times of the mass of the sun, and in order to balance the gravitational collapse, electron degeneracy exerts some kind of pressure, and the balance between this pressure exerted by electron degeneracy and the gravitational force leads to the formation of a stable star. So, once white dwarf is formed, eventually it cools down and they will die as black dwarfs. After some time, white dwarfs, because of the cooling, they will die as a black dwarfs. Okay? Now, what if the temperature is high? I am ignoring the region between 1.4 to 8 MeV, 8 mass of the times of the mass of the sun, okay? Because now I am more focused on the carbon burning, isn't it? So, at 8 to 10 times of mass of sun, if the mass is more than this and temperature is 0.6, where from you have seen this 0.6? Go here, the first one T9, 0.6. So, when temperature of the star in the core is 0.6 gigakelvin and the mass, if it is more than 8 to 10 times of mass of the sun, then the contracting core remains in non-degenerate state, and if the density is say 3 into 10 to the power of 6 grams per centimeter cube, then whatever temperature is available within the core, it is enough to ignite the carbon for burning, So, this is very important thing to know the numbers regarding temperature, density and mass corresponding to the carbon burning, all right. Now, let us go to the next stage. All of you might be expecting oxygen burning should start, because carbon, after carbon you have only oxygen, right. So, where from this neon has come? We will see. Okay. Now, if we plot mass fraction, the abundancy curve and versus time, you see here oxygen 16 is there, okay, most abundant. Of course, it is the third most abundant, and fourth most abundant element in the universe is carbon. Then you have carbon 12, then you have in between you have neon. Already we have discussed this carbon 12, right. Now, we have neon 20 and oxygen 16, but oxygen 16 is above the neon 20 plot. Then we go for magnesium, okay. Then remaining nucleides. See, at the end of core carbon burning, now hydrogen is gone, helium is gone, and ash of helium is carbon and oxygen. Because of the Coulomb barrier considerations, we were seeing carbon has to be there, right. So, this carbon burning, when it happens, the ashes are oxygen 16, neon 20, sodium 23, magnesium 24. What are the reactions which are giving this kind of which are giving this nucleides? I have shown you in the previous slides. All right. Now, see, they are inert against the photo disintegration even at high temperatures. Now, the temperature scale is going higher, right. Now, at these temperatures, either photo disintegration has to be initiated or emission of light particles, I mean the capture of lighter particles has to happen, right. However, inert against the photo disintegration, who oxygen 16, sodium 23 and magnesium 24, they are inert against the photo disintegration even at high temperatures. And the exception is neon 20. Why it is so special? Because it has a relatively small alpha particle separation energy 4.73 MeV. Remaining all they have more alpha particle separation energies. So, it is a neon which comes into picture before oxygen comes for the burning, all right. And when gamma plus neon 20 reaction happens, various possibilities are there. However, the neon 20 when it absorbs gamma, it reaches the excited state. The decay from the excited to ground state, if you find out the decay constant, how can you find out the decay constant of neon 20? Experimentally, it is very difficult to carry out gamma plus neon 20. So, what we can do is simply go for reverse reaction, all right, and then apply the reciprocity theorem and it will give you the decay constant of the neon 20. Now, so when I say reverse reaction, it could be alpha particle, it is very easy to obtain in the particle accelerator, and oxygen 16, and the reaction will give you neon 20 and gamma. Experimentally you can do this, okay. Experimentally go for alpha plus 16 oxygen gives rise to 20 neon plus gamma, all right. You measure the reaction cross section and measure the decay constant. From that we can find out it is 10 to the power of minus 6 per second. So, it will decay to alpha particles. And another possibility is when neon reacts with alpha, all right, and where from this alpha has come? From here, all right. So, initially after absorbing gamma, alpha is emitted. This alpha particle once again it can react with the neon 20, giving rise to gamma as ejectile and magnesium 24. And once again these alpha particles are available, they can react with magnesium 24, they can give rise to silicon 28. See how more and more nucleides are getting synthesized, all right. There is another possibility. So, this 23 sodium, where from it has come? In the carbon burning we have seen 23 sodium is the byproduct, and that is why I have written in this slide 23 sodium is one of the ashes of carbon burning, all right. So, when 23 sodium absorbs alpha particle, then magnesium 26 is formed and proton is emitted, and once again when alpha reacts with this magnesium 26, see all types of nuclear reactions possible in neon burning I am discussing, and it is a discussion of nuclear reactions which comprises which is the essence of this nuclear astrophysics course. So, sometimes you may feel how to remember so many reactions. No need to remember each and every reaction, but try to understand what type of reactions are happening and who is playing a major role in the synthesis of new elements. That is what is expected. Okay? And when alpha reacts with magnesium 26, you have silicon 29, and the corresponding Q values I have mentioned here, all are positive Q values. And for neon burning, the temperature region is 1.2 to 1.8. Previous one for carbon burning, it was 0.6 to 1 gigakelvin. Now, the temperature is increasing, right? Energy produced is more. So, 1.2 to 1.8 gigakelvin, if you see, that is a temperature region over which neon burning take place. And if you see the explosive neon burning, then the temperature region is 2.5 to 3 gigakelvin. So, we have reached slowly to around 2 gigakelvin for neon and 1 gigakelvin for the carbon burning. All right. Now, after neon is over, we have oxygen into picture. Same kind of diagram, mass fraction versus time. If you see, then you can observe it is oxygen 16, already have shown you this diagram. Neon is done, magnesium will come later, okay, and see the time scales. So, not this diagram is not exactly the previous one. So, in these time scales, you can see that after neon, oxygen should burn. Even you can cross check by calculating the Coulomb barriers. Okay. So, once near the conclusion of not this is oxygen, it is a core neon burning. Okay. Near the conclusion of core neon burning, the most abundant nuclei are oxygen 16, 24 magnesium and 28 silicon, and the corresponding Coulomb barrier values, if you see, it is like 15, 21 and 24 MeV. All right. Now, the fusion between heavy nuclei oxygen and oxygen, they should give rise to, of course, as expected, sulfur 32 in the excited state. And as in the case of previous neon and carbon burning, the mass difference is also high, 16.5 MeV. So, you can expect large number of overlapping energy levels, and the reaction proceeds through this overlapping energy levels. So, you have more excitation energy, you can always expect more exit channels for this oxygen plus oxygen 16. What are those? Let me quickly give you a list of the reactions possible. It can give proton, it can give you 2 protons, it can give you alpha, it can give you 2 alpha particles, it can give you deuteron, it can give you neutron. So, all these possibilities are there when oxygen and oxygen burning take place. All right. So, here you can see these two are negative Q values, endothermic, is not it. So, when this much energy is supplied, these two reactions take place, and this deuteron, when it emits, it can react with gamma, giving rise to proton and a neutron. So many possibilities are there for the emission of neutrons. Why suddenly I am discussing about neutrons? Because these are the neutrons which are responsible for the synthesis of elements beyond iron. No more charged particles. Almost all elements are synthesized beyond iron because of neutron as probes, okay, if you want to study in the laboratory. So, it is a neutron induced reactions which are responsible for the synthesis of elements beyond iron. So, where from these neutrons are coming? So, in this slide, as a part of the discussion of oxygen burning, this is one of the reactions using which, through which neutrons are emitted. Not only that, when deuterium and gamma reacts with each other, then also you will get neutrons. All right. And what are the temperature scales? It is 1.5 to 2.7 gigakelvin. See, slowly I have entered into 2 gigakelvin, and 3 to 4 gigakelvin for explosive oxygen burning, explosive oxygen burning. So, we are done with carbon burning, we are done with neon burning, we are done with the oxygen burning. Now, the last burning stage, that is silicon burning. Okay. So, see the time scale here, starting from 10 to the power of 2 to 10 to the power of 7 seconds, and mass fraction, if you see, silicon 28 is the most abundant material in these time scales. All right. So, near the conclusion of core oxygen burning. So, once oxygen is exhausted, what are the ashes? they are silicon 28 and sulfur 32, isn't it? And which one will start burning first? Of course, silicon 28 because of the Coulomb barrier considerations, isn't it? So, let us see some of the numbers regarding the silicon burning. So, silicon plus silicon 28 or silicon plus sulfur, they are too unlikely to occur because of the Coulomb barrier considerations. So, it is not like they do not occur, but it is very rarely, okay? Because if you see the Coulomb barrier for these two reactions, it is 38.7 MeV and 43.27 MeV, right. So, here also one can expect photo disintegration rearrangement process at this high temperature similar to neon burning, but on a much more extensive scale, all right. And you can see here about 4 gigakelvin the temperature scale at which the burning of silicon takes place. And for the explosive silicon burning, we can see that it is between 4 to 5 gigakelvins, all right. So, in today's lecture, I have discussed a general background of advanced burning stages within the star, carbon burning, then neon burning, not oxygen burning because of the photo disintegration, activation of photo disintegration process, then oxygen burning, and finally silicon burning. And after this silicon burnings, different types of nuclear reaction take place, finally leading to the formation of most stable nucleides, that is nucleides around iron peak. So, that framework I am not going to discuss. So, it is sufficient to understand helium burning, before that hydrogen burning, as part of which I have discussed PP chain, CNO cycle, and then helium burning, and then carbon, neon, oxygen, and silicon burning. And in the next lecture, we will see how elements are formed because of the neutrons when synthesis of elements beyond iron is considered. All right. Thank you so much for your attention. Thank you.